This lesson is 1.5 from your book. We're going to be talking about parent functions. So let's start. Parent functions, as they're called, are the simplest forms of a function in a family of functions. What the heck does that mean? So let's look at some examples. Here are some parent functions. So we see we have constant functions. That just means f of x equals a, so you plug in any x. So we plug in -8, 6, -4, -2. We get the same value. So for this example, we have 4. So that just means our f of x is just a number. So we plug in any x, we get a number. Another example is a linear function. So our parent function is f of x equals x. We have a slope of 1. Our y-intercept is 0. This is our parent function. So it's our most basic function. It's our dumbed down function. We haven't moved it at all. We have our most basic option of that function. So another linear function we could have is 2x, or 5x plus 1, or -10x minus 20. These are also linear functions, but they're versions of f of x equals x. So the way that we think about parent functions is it's the most basic function. It's the simplest form of a function in a family of functions. So all of those other linear functions, those are our family of functions. f of x equals x, that's our parent functions. So we talk about parent functions. They can be transformed to create other members in a family of functions. So that's what I was saying. We could move this f of x equals x. We could move that up and have a different. We could have another f of x equals x plus 3, maybe that's what that looks like, or we could shift it. Maybe it also still goes through the origin, but it has a greater slope, or maybe we have a negative slope when we go through the origin, or maybe we have a negative slope and we have a higher y-intercept or a lower y-intercept. These are all values. These are all transformations of our parent function. That's how we describe that. So if I were you, I would become familiar with all of these different parent functions. Maybe print this out, or just get to know all of these. We have quadratic, cubic, square root, reciprocal. These are all really good graphs to get to know what they look like, especially these sine x, cosine x, what they look like on the graph. All right, let's continue. So we can have different sorts of transformations. One sort of thing that we can have is a vertical translation. A vertical translation means the graph of g of x is equal to f of x plus k. So that's a translation of f of x translated up or down by k units. So we took this f of x plus k, which means we have f of x up or down by k units, and we ended up with g of x. So if we go back to this linear equation, if we have f of x and we added some plus k, we know that. This just means we're moving this up or down by k units. So if this was minus k, we'd move it down by k units, right? And it's obvious in a linear equation because this usually just represents our y-intercept. So if we were at 0, all right. We can also have a horizontal translation. That means we have g of x equals f of the quantity x minus h. That's a translation of the graph f of x, translated left or right by h units. Notice this is a minus, and we have it left or right. So actually, we are moving to the right by h units, and we are moving to the left by negative h units. That's super confusing. So if you have x minus 3, this moves to the right because it's already in x minus h form. So that means we would move to the right 3 units. This x minus 3 squared. We would move this x squared to the right 3 units. If we had x plus 3 squared, we would move this x squared to the left 3 units. All right. Next we can have a reflection in the x-axis. That means the graph of g of x is equal to negative f of x. That means we have a translation of the graph of f of x is reflected in the x-axis. Or you can have a reflection in the, you guys guessed it, y-axis. For that situation, the graph of g of x is equal to f of negative x. This is similar to even and odd functions, if you guys remember that. Alright, the next sort of transformation we can have is a vertical dilation, which is the graph of g of x is equal to a times f of x. That means the translation of the graph of x is compressed or expanded vertically. Or you can have a horizontal dilation, which means that the graph of g of x is equal to f of a times x. So in this situation, we're looking at this being smushed this way, that's vertical, so closer and closer and closer to the y is vertical, or being smushed this way, closer and closer and closer to x. That's horizontal. The last sort of transformation we can have is an absolute value transformation. These cause reflections. So we're looking at the sorts of things that you can do to an f of x, right? What can I do to this function in order to move this graph? What can I do to this function in order to move this graph? So the last sort of thing you can do to a function is to add an absolute value to it. What this does is cause reflections. You can cause a reflection around the x-axis if you take the absolute value of the entire function. You cause a reflection around the y-axis if you take an absolute value of just the x within the function. So f of the absolute value of x causes a reflection of the y-axis. Absolute value of f of x causes reflection around the x-axis. I'd recommend doing some practice problems and looking up some additional examples in your book or at the PowerPoint slides I have posted on Blackboard.